Thanks to Squarespace for sponsoring today's video.
Today we're going to look at a very popular question, and that is, why is the number 1 not considered a prime number? And we're going to look at this from a couple of different places. The first place will be really quick, but then we'll fill in quite a few details involving a couple of more, semi-advanced topics. Okay, so let's look at our first reason, which is going to be based off of something called the fundamental theorem of arithmetic, which I'm sure everyone is at least familiar with if you don't know its name. And that says that every natural number can be written as a unique, well, that uniqueness is up to ordering product of primes. Or perhaps we could write it like this. For all natural numbers n, there are unique primes that, well, they can be ordered, and that really means that we don't have to worry about the reordering, and that's P1 is less than or equal to P2 is less than or equal to P3 all the way up to Pk, such that n is, well, the product of those primes. So it's P1 times P2 up to Pk. Now you might say, well, this says every natural number, but what about the number 1? Well, 1 is considered to be the empty product. So that would be the product of 0 primes. So that might seem a little bit unsettling, but if you think about this in terms of a sum, it'll be a little bit better. So if you sum 0 numbers, you get the number 0, and 0 is the additive identity. Well, if you take the product of, well, an empty set of numbers, you should get the multiplicative identity, just by a parallel argument. But the multiplicative identity is the number 1. So that's how we consider 1 the empty product. And now we've got our first main reason why 1 is not considered a prime, and that is, if it were, we would lose uniqueness. For instance, we could write 20 as 2 times 2 times 5, but if 1 were prime, we could write it as 1 times 2 times 2 times 5, or 1 times 1 times 2 times 2 times 5. But notice the list of primes I used here is not the same as the list of primes I used in the second factorization, or the list of primes that I used in the third factorization. So like I said, we lost uniqueness, and that's a very nice property of this fundamental theorem of arithmetic.
Before we continue, I'd like to thank today's sponsor, Squarespace. Squarespace is a service that takes the hassle out of creating a website. You don't have to be a programmer or a graphic designer to have a professional-looking website. Because of their support, I can dedicate all of my spare time to doing the things that I love, and I have more time to focus on my mathematical research. With Squarespace, you too can focus on what's important to you and leave the technical stuff to them. The new Fluid engine gives you complete control over the structure of your website. The simple drag and drop action will get your site online quickly, and access to analytics will help you tailor your content to your audience. I use Squarespace for my website, and I find it easy to use with plenty of integrations. They even have a plugin for LaTeX that allows me to include equations on my website very easily. Whether you need a place to sell your merch or show your art, Squarespace has the tools you need to keep your website modern and easy to use. Give Squarespace a try by going to squarespace.com/MichaelPenn to save 10% off your first purchase of a website or a domain using code MichaelPenn. Thanks again to Squarespace for sponsoring today's video.
Okay, so that'll be our first reason, but in order to come up with some other reasons, we need a definition or two. Now let's build off our first reason, but like I said before, we need a definition, and that definition is something called a unique factorization domain. So that's going to be a set D with operations plus and times that essentially works a lot like the integers works. So D with plus is an abelian group, so there's an additive inverse, the addition is commutative, so on. And then the times operation is commutative, associative, and there's a distributive rule with the plus operation, like the distributive rule you know from numbers. And then also there are no zero divisors. So something's a zero divisor if, well, it's if you take two non-zero elements, multiply them together, and get a zero element. So this occurs within, for instance, like Z mod NZ, where N is a composite number. I'll let you look that up if you need to. And then the most important property of a unique factorization domain is that there is unique factorization. And we'll talk a little bit about what that means, but we need to first talk about the types of non-zero elements in unique factorization domains. So first of all, there are elements called units, and those are elements that have multiplicative inverses. So notice in the natural numbers, this is only the number 1. And so that's what makes 1 so special in the natural numbers. It is the only unit. And that's why we think it should be prime. There are tons of primes, an infinite amount, obviously. There are infinitely many composites, but there's this single number 1 that doesn't fit into either batch. But n is not a ring. It doesn't have like additive inverses. So we should really expand that to the integers. And within the integers, it's only plus and minus 1. But still, that means 1 is playing a very important role within the integers as well. Okay, so there are units. There are primes. And so a prime is a non-unit that has this, what I call forced divisibility characteristic. So if P divides A times B, then P divides A or P divides B. Note that this is not the condition that it cannot be factored. Later we'll see things that can't be factored but are not primes. And then there are composites, which is everything else. So before we talk about unique factorization more generally, I'd like to point out that here is our big other reason why we don't consider 1 to be prime. And that is because in this larger world of unique factorization domains, 1 is just one example of a unit, and no units are considered to be prime. Okay, so now to this unique factorization maybe characteristic, and this is like a pretty typical thing that happens in math, and that is you prove a property for some set or for some maybe structure, and then you define a new structure that has that property, and you look for new examples. So we, and by we I mean humanity, proved unique factorization within the integers, and they said, well, what if we had an abstract structure with unique factorization? Well, could we find other examples of such a thing? Okay, so anyway, so for all elements A in our UFD, there is a unit U and primes P1 to Pk that are unique, such that A equals the unit times the product of the primes. So again, if any unit was considered a prime, then we would no longer have a unique factorization because you could just couple that unit with its inverse over and over and over again. So really, maybe the question up here should be not why is 1 not a prime, but why are units not primes? And then the answer would be really quick, and that would be, well, we would lose uniqueness. Okay, so now that we've got all of this set up, let's look at some examples of UFDs. So to get a source of some unique factorization domains, we need something called a quadratic integer ring. So we'll start with a square-free integer, which we'll call D. And so I'm reusing D from last time. So what do I mean by square-free? Well, I mean that D is not divisible by any perfect square. I guess other than 1 squared, but that's silly. And then we'll define Z adjoin omega to be everything of the form A plus B omega, where A and B are integers, and omega is a half 1 plus square root of D if D is of the form 4k plus 1, or it's just the square root of D otherwise. And, well, this is going to break down into 2 cases, the so-called real quadratic integer rings where D is bigger than 0, and the imaginary ones where D is less than 0. Let's look at the imaginary ones first. So if D is less than 0, we don't always get unique factorization, and we'll look at some of those cases later. But we do get unique factorization in the following cases, when D is -1, -2, -3, -7, -11, -19, -43, -67, and -163. And so let's look at the first case, and that would be D equals -1. So in this case, you get something called the Gaussian integers, which are essentially like the integers within the complex numbers, Z adjoin I. Here we have 4 units instead of just 2, which we have in the normal integers, plus minus 1 and plus minus I. And then we've got primes too. Well, in fact, we have primes in all of these unique factorization domains, but here we can classify them pretty easily. We have 1 plus I is prime. Notice that 2 is not prime, and we can see that 2 is not prime because 2 is the same thing as minus I times 1 plus I squared. I'll let you multiply that out, but if you multiply this out, you'll get the number 2, meaning that 2 is no longer prime, but this 1 plus I is prime. And then all of the normal primes of the form 4n plus 3 are still prime. And those are like 3, 7, 11, 19, 23, so on and so forth. But you might say, what about the other primes, the other normal primes, I should say, which are 4n plus 1? So if P is of the form 4n plus 1 and it's prime, then by a well-known fact from number theory, we can write P as a squared plus b squared, where a and b are integers. So we can write it as a sum of squares. Any prime of the form 4n plus 1, you can do that. Oh, but look, sums of squares don't factor normally over integers, but they will factor over Gaussian integers. This means that P is equal to a plus bi times a minus bi. So there we've done it. We've factored what used to be a prime in the normal integers inside of the Gaussian integers. But these two things that are remaining are primes. And these are primes in Z adjoin I. And how could you prove that they're primes in Z adjoin I? Well, it's actually not so hard. So let's do that over here. So let's maybe make that a little claim. And the claim is, well, this statement right here. So we'll do it for a plus bi. So a plus bi is a prime inside of Z adjoin I. So how does the proof of this claim go? Well, let's suppose that a plus bi factors as z times w, where z and w are Gaussian integers. Okay, but now we're going to take the modulus of both sides. By taking the modulus of both sides, I mean we're going to multiply both sides of this equation by its conjugate. But doing that to a plus bi, we'll just retrieve p. So we have p is equal to, well, a plus bi times a minus bi. But then modulus of z times z is the modulus of z squared. Modulus of w times w is the modulus of w squared. And here we have modulus of z squared and modulus of w squared are simply integers. So we can view this, maybe extreme left and right hand side, as a factorization over the integers. So we factored p over the integers. So that means one of those terms must be equal to a unit. In other words, plus minus 1. Oh, but these are positive. So one of those has to be equal to 1 and the other one has to be equal to p. So for instance, we have modulus z squared is 1 and modulus w squared must be equal to p. But if modulus of z squared is 1, that means that z is equal to plus minus 1 or plus minus I. So in fact, we have not factored a plus bi. We factored a plus bi in some factorization that includes a unit. So that means that it is in fact prime. Okay, so now before we move on to our next little example, I'd like to take some time out right here and factor some things that used to be prime within the integers that are no longer prime in the Gaussian integers. Like a classic example would be 5, which is now 2 plus I times 2 minus I. Okay, and then another example that we could come up with pretty quickly is 41. And 41 can factor as 5 plus 4i times 5 minus 4i. That's because 25 plus 16 is equal to 41. And then you can easily come up with some other examples on your own. Okay, so let's move on to our next case when d is equal to minus. Okay, so for our next example, look at the case when z is minus 3. But notice that minus 3 is of the form 4k plus 1. So that means we need to adjoin 1/2 times 1 plus root negative 3. That's a primitive root of 3 for what it's worth. So the units here are plus minus 1 and then half plus minus 1 plus minus square root negative 3. So there are 6 total units. So 1 is even less special here, as instead of only being 2 units plus or minus 1, there are 6 total units. 3 times as many as within the integers. And then what about primes? Well, normal primes of the form 3n plus 2 are still prime. So like 2, 5, 11, 17, 23, so on and so forth. But if a prime is of the form 3n plus 1, it's no longer prime. And we can see that as follows. So if p is equal to 3n plus 1, then we have integers a and b such that the following is true. We can write p as a squared minus ab plus b squared. And this is kind of like the sum of squares thing that we saw before with Gaussian integers, just a little bit less well known. But this kind of thing factors over these integers. These are actually called the Eisenstein integers. And how does it factor? Well, it'll factor as a plus b times omega, where I'm using our definition of omega over here. And then a minus b times omega. And then just for completeness, let's recall that omega is equal to half and then 1 plus root negative 3. So, like I said, primes of the form 3n plus 1 are no longer prime. And let's just look at a couple of examples of that. So for example, 3, well, I guess 3 is not of the form 3n plus 1, but it's not of the form 3n plus 2, but this does factor. It factors as 2 plus omega times 1 minus omega. And then 7 also factors. So 7 will factor as, let's see, 3 plus omega and then 2 minus omega. So I'll let you check those if you want to. But a really important arithmetical fact here is that omega squared is equal to minus omega minus 1. That'll help you make your calculation. Okay, so, well, what did we see? We saw that in z adjoin I, there are 4 units, meaning that 1 and negative 1 are not as special there. In this set of Eisenstein integers, there are 6 units, meaning that 1 and negative 1 are not so special there either. But in fact, in all the rest of these, there are only units 1 and negative 1. So in a sense, when you look at these imaginary unique factorization domains, you almost always get kind of a boring list of units. Only in these 2 cases do you get more units. Okay, so now let's look at some real cases here. In other words, when d is bigger than 0. Okay, so now we're going to look at the case when d is bigger than 0. And in this case, you get a UFD for lots of choices of d. I think there might be infinitely many choices. And in fact, in this case, there are always infinitely many units. And so that makes 1 and negative 1 even less special. So let's look at some cases here. Let's look at the case when d is equal to 2. Here we won't classify the primes, we'll just look at the units. So notice that we have square root of 2 plus 1 times square root of 2 minus 1 equals 1. That's because 2 minus 1 is equal to 1. So that means each of these are units. In other words, square root of 2 plus minus 1, I guess it should be plus minus square root of 2 plus minus 1 are all units. And you might say, well, that just gives me 4 new units. But I can actually raise that to any power and I still get a unit. So in fact, for all natural numbers n, we have square root of 2 plus 1 raised to the n is a unit. And why is that? Well, because it's got an inverse, which is pretty easy to find. It's the square root of 2 minus 1 raised to the n power. Okay, so, well, there we've got infinitely many units. Sure, they are built out of kind of the starting unit, but we still do get infinitely many units. And then what about another case? So if d is equal to 7, well, if d is equal to 7, we can also find a couple of units. Well, notice that 8 plus 3 times root 7 times 8 minus 3 times root 7, well, that's in fact equal to 1. That's because 64 minus 63 is equal to 1. And likewise, we can take this and generate more and more and more units. So in fact, 8 plus 3 root 7 raised to the n power is always a unit. And that's because its inverse will just be 8 minus root 3 raised to the 7th power. And then of course you could get more by doing plus minus in front of everything there. We've talked a lot about places where there's unique factorization, and really that's kind of our most motivating fact to answer this question, why is 1 not prime? But that being said, let's look at a couple of places where there's not unique factorization. So just to fill in that last hole, we're gonna finish real quickly with the case where we don't have unique factorization. So here that means we'll have 4 types of non-zero elements. We'll have units and primes. We're called primes that are defined by this forced divisibility, just like we had before. We'll also have irreducibles. So irreducibles are really non-factorable. So if you factor an irreducible as a times b, then a or b is a unit. And then there's everything else. So when you have unique factorization, irreducibles and primes are the same thing. But when you don't have unique factorization, they are not the same thing. So let's look at a couple of quick examples. So in z adjoin root negative 5, 6 factors as 2 times 3, but it also factors as 1 plus root negative 5 times 1 minus root negative 5. And then you can check that 2, 3, and then 1 plus minus root negative 5 cannot be further factored, which makes them irreducible, but then this difference in factorization means that they are not primes. I'll let you show they can't be factored as a homework exercise. Here's a quick second example from z adjoin root negative 13. 22 is 2 times 11, but it's also 3 plus root negative 13 times 3 minus root negative 13. So we've looked at a lot of these quadratic integer rings, but there are definitely other types of places where there's unique factorization or maybe not unique factorization outside of these places. Do you have any favorites? Maybe post them in the comments, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.